So this is a connected mass problem, and it says we have a 6 kilogram load, so this is 6 kilograms, and a 4 kilogram block, so that's 4 kilograms up there, attached by a lightweight string that passes over a frictionless pulley of negligible mass. The block lies on a level frictionless surface, and what it wants you to find is find the tension in the string once the system is released. So let's draw this diagram in a bit more detail. So we have a 4 kilogram, and then that goes over, and we have our 6 kilogram load here. Now gravity is going to mean that we have 60 newtons there, and then of course we have the tension pulling back on the back of the 6 kilogram mass, and then we have tension pulling forwards here, and then here we have, yes, we have our 40 Newton weight, and then we have our normal force there, and remember that these two are at 90 degrees to the direction of motion. They're orthogonal to the direction of motion, so they don't play a part. They cancel each other out, but they also don't play a part in this problem. This is confusing, as we've said before, because some parts of the journey are going down and other parts of the journey are going to the right, and usually going to the right is positive and going down is negative, and you know, positive and negative for the same effect doesn't make sense. So we have 60 newtons here, we have 6, we have 4, we have our tension here, and we have our tension there. No force backwards here because there's no force in the direction of motion that's retarding this behavior. And I want to find the tension. It's definitely a Newton's second law question, and I could look at the 4 kilogram mass, or I could look at the 6 kilogram mass. If I looked at the 6 kilogram mass, I'd take into account that 60 and that tension, because it's net external forces. If I want to look at the 4 kilogram mass, it's only this tension pulling on it. That seems to be the best bet. I'll say find T using the sum of the forces of the 4 kilogram mass equals the mass of the 4 kilogram mass times the acceleration of the 4 kilogram mass. That's my shorthand to remind me of which part of the diagram I'm using. And then I'll say, well, looking at my diagram, I say plus T, that's the only external force acting on that 4, is equal to the 4 times the acceleration. The problem is, of course, I don't know what that acceleration is, so this becomes a two-part problem. So I say, okay, find A using, and the trick is to know that I find A using the sum of the forces on the system equals the mass of the system times the acceleration of the system. And just so we get our diagram right, my system is those two masses connected together and treated as one thing. So that's 4 and that's 6, and my tensions are internal to this system, so I don't worry about these guys. They're not, it's like sitting in your car and pushing on your dashboard and expecting to accelerate forwards. It's not going to happen because that's an internal force. So looking at my diagram, I say, well, there's my 60, I'm sorry, there's my 60. So I say plus 60 is equal to 4 plus 6 times A. So A is going to equal plus 60 over 10, which equals plus 6 meters per second squared. That's the acceleration of the system, and the acceleration here is the acceleration of the 4 kilogram mass, but they're the same. So this equals 4 times plus 6 which equals 24 newtons. So I simply take the acceleration for the system, and I recognize that that's the same as the acceleration for the 4 kilogram for the 4 kilogram mass, and then I say okay, F equals ma.